Hi, today we're going to learn about the gas laws. On this page, I am going to give you an overview of all the equations used in the computations. Like solids and liquids, gases are also made up of atoms. The main difference is that gases are highly compressible. Therefore, it is easy to make predictions about the properties and behavior of gases if you know the following four variables. First, we have the amount of gas in terms of the number of moles. This is represented with a small letter n. Next, we have the temperature. The kinetic energy of a gas molecule increases as the temperature increases. Note that all measurements will have to be converted to Kelvin before calculations. We also have pressure. Since pressure in a container is created by collisions of molecules on the walls of the container, it is important to know the relative pressure of a system. Finally, we have volume. Remember that a gas will fill any container, and the volume is usually measured in liters. This equation in the box is known as the ideal gas law equation. Pressure times volume equals the amount of gas in moles times the gas constant R times the temperature. Right above here, we have the equation for Boyle's law. Down below, we have the equations for Charles' law and Gay-Lussac's law. We also have the combined gas law equation and the Avogadro's gas law equation. Here are two of the most common gas constant values, and these values are actually dependent on the unit of the pressure used. And here's how to calculate the temperature into Kelvin. Take the amount in degrees Celsius, add 273, and you now have the temperature in terms of Kelvin. Out of all the variables mentioned, the pressure perhaps is the least familiar, so let us discuss it here. Pressure is defined as the force per unit area pressing against a surface. Mathematically, it is represented as P for pressure equals F for force divided by A for area. Here are some common units for pressure. 1 atmosphere is equal to 760 millimeter mercury, and that's also equivalent to 14.7 pounds per square inch and 101,325 pascals. 1 millimeter mercury is equal to 1 torr and also equal to 133.32 pascals. This one right here is the pressure gauge used in gas cylinders. Units are usually in pounds per square inch, the red ones, and the bar, the ones in black. This is a sphygmomanometer. The BP app usually measures systolic and diastolic blood pressure in terms of millimeter mercury. We also have the barometer, which measures atmospheric pressure in millimeter mercury or hectopascals. Let us now take a look at the gas laws individually. The first one is Boyle's law. For a fixed mass of an ideal gas at a constant temperature, the volume of the gas is inversely proportional to the applied pressure. What do we mean by inversely proportional? As the volume increases, the pressure decreases. For example, if the volume doubles, the pressure decreases by 1/2. The equation for Boyle's law is initial pressure times initial volume equals final pressure times final volume. For us to be able to understand this law better, here is a graph. On the x-axis, we have the pressure in atmospheres, and on the y-axis, we have the volume in liters. At this point, the volume of the gas is 2.5 liters, and the corresponding pressure is 4.0 atmospheres. If we double the volume to 5 liters, the corresponding pressure is equal to 2.0 atmospheres. From 4.0, it has been reduced to half. And also at this point, when the volume is 10 liters, the corresponding pressure is now only 1.0 atmospheres. So, from the graph, you would see that as the volume increases, the pressure decreases. So that is what we mean by an inverse relationship. Next, we proceed with Charles' law. At constant pressure, the volume of a fixed amount of gas is directly proportional to its Kelvin temperature. It means that as the temperature increases, the volume also increases. And for example, if the temperature doubles, the volume also doubles. The equation for Charles' law is initial volume divided by initial temperature equals final volume divided by final temperature. And for us to be able to understand this Charles' law better, here is a graphical representation. On the x-axis, we have the temperature in Kelvin, and on the y-axis, we have the volume in milliliters or ml. At this point, temperature is 150 Kelvin and the volume is 300 ml. So what happens if we double the temperature to 300 Kelvin? The corresponding volume also doubles to 600 ml. Third, we have Gay-Lussac's law. At constant volume, the pressure of a fixed amount of gas is directly proportional to its Kelvin temperature. This means that as the temperature increases, the pressure also increases. For example, if the temperature doubles, the pressure also doubles. Here is our equation for this law. Initial pressure divided by initial temperature equals final pressure divided by final temperature. Here is a graphical representation. On the x-axis, we have the temperature in Kelvin, and on the y-axis, we have the pressure in atmospheres. At this point, the temperature is 150 Kelvin, and the corresponding pressure is 1.5 atmospheres. So what happens if we double the temperature to 300 Kelvin? The corresponding pressure also doubles to 3.0 atmosphere. Let us proceed to the combined gas law. Since pressure times volume, volume divided by temperature, and pressure divided by temperature, from the previous gas laws discussed, all have constant values for a fixed amount of gas. These relationships can be merged into a single combined gas law, which holds true whenever the amount of gas is fixed. The chemical equation for the combined gas law is this one. Initial pressure times initial volume divided by the initial temperature equals final pressure times final volume divided by final temperature. Next, we have the ideal gas law. The relationships among the four variables, pressure, volume, temperature, and number of moles for gases, can be combined into a single expression called the ideal gas law. And that is equal to pressure times volume equals number of moles times the gas constant R times the temperature. Take note that the gas constant has a specific value depending on the unit of pressure used. Now, let us take a look once more at all the equations for the gas laws. Well, we really only have to remember the ideal gas law equation, and from this, we can derive the other equations for the other gas laws. So for the ideal gas law equation, pressure, usually in the units of atmosphere or millimeter mercury, times volume in liters, equals the amount of gas in number of moles times the gas constant R times the temperature in Kelvin. For Boyle's law, remember that it states that the pressure is inversely proportional to the volume. So how would we remember the equation for Boyle's law? If we look at the ideal gas law, pressure and volume are found on the same side of the equation, on the left side of the equal sign. And so for the Boyle's law equation, it would involve multiplication. Initial volume times initial pressure equals final volume times final pressure. If we take a look at Charles' law, which states that the volume and the temperature of the gas are directly proportional to each other, which means that as the volume increases, the temperature also increases. How do we remember this equation? If we look at the ideal gas law equation, volume is found on the left side of the equation, whereas temperature is found on the right side of the equation. So in the Charles law equation, it would involve division. Initial volume divided by initial temperature equals final volume divided by final temperature. Similarly, the equation for Gay-Lussac's law would involve division. Why? Because if you look into the ideal gas law equation, pressure is found on the left side of the equal sign, and temperature is found on the right side of the equal sign. And so, the equation for Gay-Lussac's law would involve division. Initial pressure divided by initial temperature equals final pressure divided by final temperature. And what does this tell us? It tells us that pressure is directly proportional to temperature, meaning as pressure increases, the temperature would also increase. If we combine the Boyle's law, Charles' law, and Gay-Lussac's law together, we have this combined gas law equation. Initial pressure times initial volume divided by initial temperature, and that is equal to final pressure times final volume divided by final temperature. We also have Avogadro's law, which states that equal volumes of gases at the same temperature and pressure contain equal number of moles. So looking into the ideal gas law equation, volume is found on the left side of the equal sign, and the amount of gas in moles is found on the right side of the equal sign. So the Avogadro's law equation would entail division. So initial volume divided by the number of moles initially equals final volume divided by the final number of moles. And so some reminders, here are the values for the gas constant that we would frequently use depending on the unit of the pressure. And of course, whenever we do temperature calculations, the temperature must be expressed in terms of the Kelvin unit. Let us now proceed to some sample problems. For our convenience, I have placed all the gas law equations here on the lower right side of this slide. Well, actually, it really doesn't matter if you don't remember the name of the gas law, as long as you know which equation to use for a particular problem. And I hope to be able to show you how. So for sample problem number 1, the volume of a balloon is 3.45 liters at 1.00 atmosphere. What pressure is required to compress the balloon to a volume of 1.25 liters? First thing to do is to identify the given in the problem. So we have 3.5 liters for volume and 1.00 atmosphere for the initial state. So we write V sub 1 equals 3.45 liters and P sub 1 equals 1.00 atm for atmosphere. 1.25 liters here is the final volume. So we write V sub 2 equals 1.25 liters. And of course, we are looking for the pressure, particularly the final pressure, P sub 2. Now, how do we know which equation to use? Notice that in the given, we are dealing with pressure and volume. So we look at the equations here. Which equation involves pressure and volume? This one. So that is what we're going to use. Well, it's actually Boyle's law, if you remember. Oh, but before that, knowing that for Boyle's law, pressure and volume are inversely proportional to each other. So let us take a look at the given. The volume is decreased from 3.45 liters to 1.25 liters. So since the relationship is inverse, we would expect an increase in pressure. So let us take a look at the solution. From the formula, initial pressure times initial volume equals final pressure times final volume, we would want to solve for P sub 2, or the final pressure. So what do? We divide both sides of the equation by V sub 2. So this side of the equation divided by V sub 2, and this side of the equation also divided by V sub 2. That way, we are not changing anything about the equation. And notice that V sub 2 here is present both in the numerator and the denominator, so that cancels out. And that leaves us with a working equation, which is P2 or P sub 2 equals V sub 1 times V sub 1 divided by V sub 2. All these values are found in the given, so we could directly substitute. Initial pressure is 1.00 atmosphere, initial volume is 3.5 liters, and final volume is 1.25 liters. So if we do this in the calculator, we would arrive at the answer of 2.76 atmospheres. Sample problem number 2. A sample of sulfur dioxide gas has a volume of 5.5 liters. It is heated at constant pressure from 35.0 degrees Celsius to 95.0 degrees Celsius. What is the new volume? First thing to do is identify the given. 5.5 liters here is the initial volume. And we see that in the problem, the gas has been heated from this initial temperature of 35.0 degrees Celsius to 95.0 degrees Celsius. So this is our T sub 1 and this is our T sub 2. Remember that for temperature calculations, we would always have to convert it into Kelvin. So here are the new values for T sub 1, 308 Kelvin, and for T sub 2, 368 Kelvin. We are looking for the final volume. So looking at the given, it involves volume and temperatures. So what equation can we use? We would use that equation which also involves volume and temperatures. So this one. This is actually Charles' law. And if you remember, volume and temperature are directly proportional to each other according to Charles' law. So we see that the temperature has been increased, and so we would also expect an increase in volume. From the formula given, the first thing to do is what you call the cross multiplication. So initial volume times final temperature equals final volume times initial temperature. Our unknown here is V sub 2, so we want to solve for V sub 2. What do? Is that we divide both equations by T sub 1. So for this side of the equation, V sub 2 times T sub 1 divided by T sub 1. And on this side of the equation, V sub 1 times T sub 2 divided by T sub 1. Notice that T sub 1 on this portion would cancel out. And so we are left with the working equation, which is V sub 2 equals V sub 1 times T sub 2 divided by T sub 1. All these values are found in the given, so we could do direct substitution. V sub 1 is 5.5 liters, T sub 2 is 368 Kelvin, and T sub 1 is 308 Kelvin. So if we do this in the calculator, the answer would be 6.6 liters. Units Kelvin here in the numerator and the denominator would cancel out. So indeed, since there's an increase in temperature, there's also an increase in volume. That is our Charles' law. Let us now proceed to sample problem number 3. A glass laboratory flask is filled with gas at 30.0 degrees Celsius and 0.95 atmosphere pressure, sealed and then heated to 120 degrees Celsius. What is the pressure inside the flask? So let's identify the given. We have the initial temperature, which is 30.0 degrees Celsius, the initial pressure, which is 0.95 atmosphere, and the final temperature, which is 100 degrees Celsius. So remember that for temperatures, we have to convert it into the Kelvin unit. So initial temperature would be 303 Kelvin, and final temperature would be 393 Kelvin. Notice that in the given, we have values for temperature and pressure. So looking at the equations here, what can we use? Yes, we can use this one because it involves pressure and temperature. This is actually Gay-Lussac's law, which tells us that pressure and temperature are directly proportional to each other. So here we could see an increase in temperature, so we are also expecting an increase in pressure. Let us take a look at the solution. So from the Gay-Lussac's law equation, we do cross multiplication. P sub 1 times T sub 2 becomes equal to P sub 2 times T sub 1. Since we are looking for P sub 2, we divide both equations by T sub 1. That way, we are not doing anything or changing anything about the equation. So notice, on this side of the equation, T sub 1 cancels out. And so we are left with a working equation that is P sub 2, which is equal to P sub 1 times T sub 2 divided by T sub 1. All these values are found in the given, so we could do direct substitution. Initial pressure is 0.95 atmosphere. Final temperature is 393 Kelvin, and initial temperature is 303 Kelvin. The units Kelvin here would cancel out. And if we do this in the calculator, we would get an answer of 1.2 atmospheres. So indeed, since pressure and temperature are directly proportional to each other, we increase the temperature, we also increase the pressure. Next, we have sample problem number 4. A gas occupies 0.266 liters at 725 torr and 30.0 degrees Celsius. What will be its volume at STP? First, let us write down the given in the problem. Initial volume is 0.266 liters. Initial pressure is 725 torr. And temperature is 30.0 degrees Celsius. We are looking for the final volume at STP. So, what do we mean by STP? This is the standard temperature and pressure. Well, actually, STP is a standard from which the properties of gases are determined. And here are the values. The pressure is 1 atmosphere, or 760 millimeter mercury, or also equal to 760 torr. Temperature is 273 Kelvin, or 0 degrees Celsius, and the volume at STP is 22.4 liters. Again, this is the standard temperature and pressure from which the properties of gases are determined. So, from this, we could get the values for final pressure and final temperature. So, final pressure is 760 torr, because 760 torr is also equal to 760 millimeter mercury. And the value for temperature is 273 Kelvin. And we are looking for V sub 2. So, in the given, we have values for volume, pressure, and temperature. So, looking at the equations here, we could use this one because it also involves values for pressure, volume, and temperature. This is actually the combined gas law. So let us take a look at the solution. So from the combined gas law, we still do cross multiplication. P sub 1 times V sub 1 times T sub 2, and that is equal to P sub 2 times V sub 2 times T sub 1. And since we are looking for V sub 2, we divide both sides of the equation by P sub 2 and T sub 1. So on this side, we see that the T sub 1 and P sub 2 would cancel out, leaving us with a working equation of V sub 2, and that is equal to P sub 1 times V sub 1 times T sub 2 divided by P sub 2 times T sub 1. All these values are found in the given, so we could do direct substitution. Initial pressure is 725 torr. Initial volume is 0.266 liters. Final temperature is 273 Kelvin. Final pressure is 760 torr, and initial temperature is 303 Kelvin. So the units Kelvin and torr would cancel out, leaving us with a unit of liter. And if we input this in the calculator, we would arrive at an answer of 0.229 liters for the final volume. Let us now proceed with sample problem number 5. If 2.65 moles of helium has a volume of 0.150 L at 294 Kelvin, what is the pressure in atmospheres? Let's list down the given. For N, we have 2.65. For volume, we have 0.150 liter. And for temperature, we have 294 Kelvin. We are looking for the pressure. So we have values for N, V, T, and we are looking for P. So that gives us a hint that we should be using this ideal gas law equation. Now from the formula, P times V equals N times R times T, we are going to solve for P. So we divide both sides of the equation with V. Notice that V here on this side of the equation would cancel out, and that leaves us with the working equation, which is P equals N times R times T divided by V. All these values are found in the given, so we could do direct substitution. N equals 2.65 moles. R is our gas constant, and so since our pressure we want it to be in atmospheres, so we make use of this gas constant, 0.0821 liter atmosphere per mole Kelvin. And then for temperature, we have 294 Kelvin, and for volume, we have 0.150 liter. So notice the units liter will cancel out, mole will also cancel out, as well as Kelvin. That leaves us with the unit of atmosphere. So in the calculator, 2.65 times 0.0821 times 294, and then divided by 0.150, we would get an answer of 426, and the unit is in atmospheres. So finally, we proceed with Dalton's law of partial pressure. According to this law, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressure of the gases in the mixture. So it is represented with this equation. P sub T means total pressure, and you see that it is equal to the sum of the partial pressures of the gases involved in the mixture. Let's have a sample problem. A gas tank contains 1.3 atmospheres of nitrogen gas and 2.5 atmospheres of oxygen gas. What will be the total pressure of the mixture? So we have the given pressure for nitrogen gas is 1.3 atmosphere, and pressure for the oxygen gas is 2.5 atmospheres. So according to Dalton's law of partial pressure, the total pressure is just equal to the sum of these partial pressures of the individual gases found in the mixture. So it's just 1.3 atmospheres plus 2.5 atmospheres, and that will give us a total of 3.8 atmospheres. So there you have it. That would be all for the gas laws and Dalton's law of partial pressure. Thank you and have a great day.